So dear students, in my last video, I have explained the classification of refrigeration cycle and I have started the reverse Carnot cycle. So in this air refrigeration, vapor refrigeration system, air refrigeration reversed Carnot cycle, reversed Brayton cycle or Bell-Coleman cycle. Vapor refrigeration, vapor compression refrigeration system, vapor absorption refrigeration system. So in my last video, I have completed this. And in my previous videos, if you check reversed Brayton cycle or Bell-Coleman cycle, this is also completed. So in one of my videos, I have explained the conditions in vapor compression refrigeration system, but I have to add some more things in the vapor compression refrigeration system. Today in this video, we will see vapor compression refrigeration system in detail. So this is what the last class we have seen the air refrigeration. Now we'll move on to vapor compression refrigeration system. So in this vapor refrigeration system, so there will be 4 different conditions. The first one is dry saturation refrigerant at the beginning of compression. So this condition should be satisfied. Dry saturation refrigerant at the beginning of compression. That means at the beginning of compression, before starting the compression, it should be dry saturated. So we need to draw the temperature entropy and pressure enthalpy. So this is temperature entropy and this is pressure and this is enthalpy. So always remember temperature entropy. So lines you have to draw like this. So in this, so dry saturation refrigerant at the beginning of the compression, so it should be dry saturated. This is the dry saturation line. This is the water line. So the dry saturation line at the beginning of the compression start from here. So 1 to 2 process is isentropic process. Entropy remains constant. This goes to superheated region. If you cool the gas or vapor, so it will condense and will come back to the dry saturation, and then if you further cool or condense, so it will come back to the water region, which is third region, and then if you still condense, so it will become the wet steam. This is the wet steam region 4, and then it will come back to the dry saturation region. So this is what the cycle goes. So you can take this as 2 dash, where after condensing it touches the dry saturation line. So if you look at it, so this is the evaporator, this is the condenser, this is evaporator, compressor, condenser and throttle valve. Okay, in the same way if you draw, so pressure enthalpy has to be drawn like this. There is a dome shape. Okay, so this is a dry saturation line. So if it goes to the superheated region 1 to 2, and then it will come back, it gets condensed, it will come back to 2 dash, and then it will come to water region. This is 3, and then throttling process, it is straight, which is nothing but 4. So from 3 to 4 is throttling process, again 4 to 1. Okay, so this is the pH diagram: pressure, enthalpy and temperature entropy. Okay, so this is 1 to 2 is compressor, and 2 to 3 condenser, 3 to 4 throttle valve or expansion valve, and 4 to 1 is evaporator, where the cooling effect takes place. So this is the place where cooling effect takes place. So we can take it as refrigerating effect. So again, this is the place where cooling effect takes place. This is taken as refrigerating effect. So this is the place where compressor work takes place. So this is the compressor work. So we can write it as compressor work. Alright. So now how to take the enthalpies? Okay, right, H1 is equal to, so from here this is the H1. So how to take this one? H1 is equal to Hg at T1 temperature, at T1 temperature. Again H2, so this is the H2. So H2 should be taken as Hg plus Cpg, this portion is nothing but T2 minus T2 dash. So H2 is equal to Hg plus this portion is nothing but Cpg into T2 minus T2 dash. This is the H2. And the H3 region. So this is the H3 region, or H3 is equal to H4. Okay, I have to take it as HF of T2 temperature. This is at T2 temperature. This is at T1 temperature. Alright, this is Hg at T2 temperature because it is at 2 temperature. So COP is equal to refrigerating effect divided by net work done is equal to refrigerating effect divided by, so what is the work done here? So compressor. So compressor work. So H1, see, refrigerating effect is equal to H1 minus H4 divided by compressor is equal to H2 minus H1. Okay, so H1 is equal to, where H1 is equal to Hg at T1 temperature. H1 is equal to Hg at T1. This is the T1 temperatures and this is T2 temperature. So Hg at T1 temperature. Next H2 is equal to Hg or at T2 temperature, at T2 temperature plus Cpg into T2 minus T2 dash. Next H3 is equal to Hf at T2 temperature, and H4 is equal to Hf at T2 temperature because this both are same. H3 is equal to H4. So this is the dry saturation. So second condition is wet compression. Wet compression in the sense, so during compression process it should be in wet region. This is the wet region or this is the wet region. So it should be, this one point should be inside this dry saturation line. This is the dry saturation line. If you draw the diagram, you will clearly understand. So this is temperature, this is entropy, and this is pressure, and this is enthalpy. Alright. So if I draw the diagram, so it should start from here, right? First point, because this is the wet region. So this is the first point. From here it will go to the dry saturation. This is 2, and then it will come back to the water region 3, and then so it will come back to the fourth region or wet region again, wet steam 4, and go back to the wet region again. So this is the diagram. So if you look at it, so this is the refrigerating effect RE. The same thing if you draw in temperature entropy diagram, temperature enthalpy, sorry, pressure enthalpy. This is temperature entropy, this is pressure enthalpy. So if you should start from here, first point, and then go to the second point, and then third point, and then fourth should be isenthalpy, it should be straight. So 1, 2, 3 and 4. Okay, so this is the line. So where the refrigerating effect takes place, this is the refrigerating effect takes place. And 1 to 2 process is nothing but compressor work. So it is taken as, so I'll draw a double hatch line which indicates compressor work. Okay, so I will write clearly here. So in wet compression, refrigerating effect reduces, but compressor work increases. Alright, so wet compression, in wet compression RE reduces, refrigerating effect reduces, compressor work increases. If you look at the diagram, you will clearly understand refrigerating effect decreases and compressor work increases. This is what I have written the statement here. Refrigerating effect reduces, compressor work increases. So therefore COP will be less when compared to dry compression, because if this reduces and this increases, obviously COP will become less. So we will see the enthalpy is H1 is equal to HF plus X into HFG. So at T1 temperature, where X is equal to dryness fraction. So all these things have been studied in your first level of engineering, that is first year of engineering, in steam chapter. H1 is equal to HF into HF plus X into HFG. H2 is equal to Hg at T2 temperature, and H3 is equal to HF at T2 temperature, same as that of H4. So only difference is H1. H1 will start from wet region. Wet region there will be some dryness fraction. So HF plus X into HFG. H2 is lying on the dryness fraction. So Hg at T2 temperature. So H3 is equal to HF at T2 temperature. So this is the condition for wet compression and wet compression. So when it starts from, so first region should be below that of dry saturated line. Thank you.